try something for me. Look at a clock. Any clock, the one on your wall, the one on your phone, the little digital readout blinking on your microwave. Watch the seconds tick by. 1, 2, 3. Each interval feels identical to the last, doesn't it? A metronome of reality, clicking along with perfect mechanical indifference. You've watched clocks your entire life, and in all that time, you've probably never once questioned whether those ticks were telling you the truth. Why would you? A second is a second is a second. Time flows like a river, steady, universal, the same for everyone standing on its banks. Except it doesn't. That clock on your wall is lying to you, or rather, it's telling you a version of the truth. Your version. And your version, it turns out, is not the same as everyone else's. The person driving past your house right now, the pilot cruising at 37,000 feet above you, the astronaut orbiting the Earth at 17,000 miles per hour, they each have their own clocks, and those clocks, if you could compare them with extraordinary precision, are not ticking at the same rate as yours. The differences are unimaginably small at the speeds of everyday life. Billionths of a second, trillions. But they are real, they are measurable, and they are not a flaw in the clocks. They are a feature of the universe. This is the strange, beautiful, and deeply unsettling truth that Albert Einstein uncovered at the beginning of the 20th century, first in 1905 with his special theory of relativity, and then a decade later with his general theory of relativity. Together, these two frameworks constitute what many physicists consider the single most profound reimagining of reality in the history of human thought. Not because they gave us new equations, though they did. Not because they made predictions that were later confirmed, though that happened too. But because they reveal that the stage on which all of physics plays out, space and time themselves, is not what we thought it was. It is not fixed. It is not rigid. It is not the same for everyone. It bends. It stretches, it warps, and it does so in ways that are determined by something deceptively simple, how you are moving and where you are. But let's not get ahead of ourselves. Before we can understand how Einstein dismantled our intuitions about time and space, we need to understand what those intuitions are and where they came from. Because the story of relativity is, in a very real sense, the story of humanity waking up from a dream it didn't know it was having. For most of recorded history, the way humans thought about motion was, frankly, a mess. Aristotle believed that objects moved because they had an innate desire to reach their natural place. Heavy things fell because they wanted to be near the center of the earth, and light things like fire rose because they wanted to be near the heavens. It took nearly 2,000 years for someone to seriously challenge this picture, and that someone was Galileo Galilei. Galileo didn't just look at the world differently. He insisted on testing it. He rolled balls down inclined planes. He dropped objects from towers, or so the legend goes. And he arrived at a principle so simple and so powerful that it became one of the foundations of all modern physics. If you are moving at a constant speed in a straight line, there is no experiment you can perform, no measurement you can make, no observation you can record that will tell you whether you are moving or standing still. Think about that for a moment. Imagine you're inside a perfectly smooth train car with the windows blacked out and no vibrations from the tracks. You set a ball on the floor. It doesn't roll. You pour a glass of water. The surface is perfectly level. You toss a coin into the air and it lands right back in your hand exactly as it would if you were standing in your living room. There is no way, absolutely no way, to determine from inside that train car whether you are moving at 100 miles per hour or sitting perfectly still on a siding. This is Galilean relativity, and it tells us something profound. Constant velocity is physically meaningless in an absolute sense. Motion only has meaning relative to something else. And this, incidentally, is why your coffee sloshes. When you're walking at a steady pace with a cup of coffee, the coffee is, in a sense, perfectly happy. It's moving along with you, and from its perspective, if coffee could have a perspective, everything is peaceful. But the moment you change your pace, the moment you speed up or slow down or turn a corner, you are accelerating. And acceleration is something that coffee can detect. The liquid, thanks to its inertia, wants to keep moving in the direction it was already going, at the speed it was already traveling. Your hand, connected to the cup, changes course. but the coffee hasn't gotten the memo yet. So it surges forward, or sideways, or sloshes up over the rim and onto your shirt. You curse. You dab at the stain. But what you've actually just witnessed is a tiny, mundane demonstration of one of the deepest principles in all of physics. The distinction between constant motion and acceleration. The very distinction on which the entire edifice of relativity is built. Now, Galileo's insight was revolutionary, but it left an enormous question unanswered. A question that wouldn't fully surface for another 2.5 centuries. If all constant motion is relative, and no experiment can distinguish between being at rest and being in uniform motion, then what about light? By the 19th century, physicists understood light to be a wave. James Clerk Maxwell had shown through his magnificent set of equations that light was an electromagnetic wave, a self-propagating ripple in electric and magnetic fields that traveled at a very specific speed, approximately 299,719.72 kilometers per second. But waves, as everyone knew, needed a medium. Sound waves travel through air. Ocean waves travel through water. So what was light traveling through? The answer, physicists believed, was a substance called the luminiferous ether, an invisible, all-pervasive material that filled every corner of the universe and served as a medium through which light propagated. The ether was a comforting idea. It restored a kind of absolute reference frame to the universe. Even if you couldn't tell whether you were moving by tossing a ball inside a train, you could tell, in principle, by measuring the speed of light. If you were moving through the ether, then light traveling in the direction of your motion should appear slightly slower, and light traveling against your motion should appear slightly faster, just as a swimmer moving with a current covers ground more quickly than one swimming against it. All you needed was a sufficiently precise measurement, and you could detect the Earth's motion through the ether. You could find the one true rest frame of the universe. In 1887, 2 American physicists set out to do exactly that. Albert Michelson and Edward Morley designed what has become one of the most famous experiments in the history of science. Their apparatus, called an interferometer, split a beam of light into 2 perpendicular paths, sent them bouncing off mirrors, and then recombined them. If the Earth were moving through the ether, the 2 beams would travel slightly different effective distances, and when they were recombined, they would be out of step. They would produce an interference pattern that shifted as the apparatus was rotated. The expected shift was small, but Michelson's instrument was extraordinarily sensitive, capable of detecting differences far smaller than what the ether theory predicted. They found nothing. No shift, no difference. No matter how they oriented the apparatus, no matter what time of day or year they performed the experiment, the speed of light was the same in every direction. The Earth's motion through the supposed ether produced absolutely no detectable effect. It was as if the ether didn't exist. Or, more precisely, it was as if the speed of light didn't care how the observer was moving. This result was, to put it mildly, a crisis. Physicists tried everything to explain it away. The great Dutch physicist Hendrik Lorentz proposed that objects moving through the ether physically contracted in their direction of motion by exactly the right amount to cancel out the expected shift. The Irish physicist George Fitzgerald independently proposed the same idea. These Lorentz Fitzgerald contractions could save the ether, but at a cost. They were ad hoc, a patch stitched onto the theory to make it work, with no deeper justification. It took a 26-year-old patent clerk in Bern, Switzerland, to see what everyone else had missed. In 1905, Albert Einstein published a paper with the unassuming title On the Electrodynamics of Moving Bodies, and in it, he didn't try to save the ether. He didn't try to explain why the Michelson-Morley experiment gave a null result. Instead, he did something far more radical. He took the null result at face value and asked, what if the speed of light really is constant for all observers? What if that's not a problem to be solved, but a principle to be embraced? Einstein's special theory of relativity rests on just 2 postulates. 2? That's it. The first is essentially Galileo's principle of relativity, updated for the modern age. The laws of physics are the same in all inertial reference frames. An inertial reference frame is simply one that isn't accelerating. It's moving at a constant velocity. This postulate says that no inertial frame is special. There's no experiment you can do to determine whether you are truly at rest or truly in motion. All uniform motion is relative. The second postulate is the bombshell. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. It doesn't matter if you're running toward the light or away from it. It doesn't matter if the source is moving toward you or away from you. You will always measure the speed of light to be exactly the same value, roughly 300,000 kilometers per second. Now, this second postulate is the one that breaks people's brains, and rightly so, because it flatly contradicts everything we experience in everyday life. If you're standing on the sidewalk and a car passes you at 60 miles per hour and the driver throws a ball forward out the window at 20 miles per hour, you see the ball moving at 80 miles per hour. Velocities add. That's just common sense. But if the driver turns on the headlights instead, and you measure the speed of the light coming from those headlights, you don't get the speed of light plus 60 miles per hour. You get exactly the speed of light. And the driver measuring the light from inside the car also gets exactly the speed of light, the same value, for both of you, even though you are moving relative to each other. This is not intuitive. This is not common sense. And it has consequences that are, to borrow a word from Einstein's own correspondence, astounding. To see why, let's conduct a thought experiment, one that physicists have used for over a century to make the implications of special relativity vivid and undeniable. It's called the light clock. Imagine a clock that works like this. A single photon, a particle of light, bounces back and forth between two mirrors, one at the top and one at the bottom, separated by some fixed distance. Every time the photon completes one round trip up to the top mirror, back down to the bottom mirror, the clock ticks. It's a beautifully simple device, and because it uses light whose speed we know is constant, it gives us a perfectly reliable measure of time. Now, imagine this light clock is sitting on a spaceship, and you're standing outside watching the ship fly past you at some significant fraction of the speed of light. On the ship, the passengers see nothing unusual. The photon bounces straight up and down between the mirrors, just as it always has. Tick, tick, tick. But from your perspective outside the ship, something very different is happening. Because the ship is moving horizontally while the photon is bouncing vertically, the photon isn't traveling straight up and down anymore. It's tracing a diagonal path, up and to the right, then down and to the right, a zigzag. And here's the key. The photon is still traveling at the speed of light. It has to. That's Einstein's second postulate. But the diagonal path is longer than the straight vertical path. Think of it geometrically. If the vertical distance between the mirrors is one side of a right triangle and the horizontal distance the ship moves during one tick is the other side, then the diagonal path the photon follows is the hypotenuse. And the hypotenuse of a right triangle is always longer than either of its sides. So the photon, traveling at the same speed but covering a longer distance, takes more time to complete each tick of the clock as you observe it from outside. The clock on the spaceship, from your perspective, is running slow, not because it's broken, not because of some mechanical flaw, but because the geometry of space and the constancy of the speed of light conspire to make it so. Time itself for the moving ship passes more slowly than it does for you. This is time dilation, and it is not a trick, not an illusion, not a quirk of perception. It is a fundamental feature of the universe. The passengers on the ship, meanwhile, notice nothing unusual. Their clock ticks at its normal rate. Their hearts beat at their normal pace. Their conversations unfold at their normal rhythm. They are not experiencing slow motion. From their perspective, they are perfectly stationary. It's you who are moving past them at high speed, and if they could peer out and observe a light clock sitting in your living room, they would see your clock running slow. This perfect symmetry is a hallmark of special relativity. Each observer sees the other's clock as running slow, and both are equally correct. There is no objective God's eye view of time that settles the dispute. There is no universal clock ticking away in some cosmic clock tower, parceling out seconds equally to all observers. There is only perspective. The mathematics of time dilation are captured by a single, elegant equation involving what physicists call the Lorentz factor, denoted by the Greek letter gamma. Without writing out the formula, here's what it tells you. At everyday speeds, the speed of a car, a plane, even a rocket, the dilation effect is vanishingly small. A billionth of a second here, a trillionth there. But as you approach the speed of light, the effect grows without bound. At 90% the speed of light, a moving clock ticks at about half the rate of a stationary one. At 99%, it ticks at about 1/7 the rate. At 99.999%, a moving clock barely ticks at all. And at the speed of light itself, the equation tells you something remarkable. Time stops entirely. A photon traveling at the speed of light does not experience the passage of time. From its own perspective, insofar as we can even use that word, a photon emitted from a star 8 billion light years away and absorbed by your retina arrives at the instant it was born. Its entire journey from our perspective spanning billions of years is, from its own perspective, instantaneous. Let that sink in for a moment. The light entering your eyes from the most distant galaxies has not, from its own frame of reference, aged a single moment. The universe is full of photons that are, in some profound sense, timeless. But time dilation, stunning as it is only the beginning. Because Einstein's two postulates don't just change how we think about time. They change how we think about everything, including something as seemingly straightforward as the question of whether two things happen at the same time. In everyday life, simultaneity seems like an objective fact. If two firecrackers go off at the same moment in a field, they go off at the same moment, period. It doesn't matter where you're standing, how fast you're moving, or which direction you're looking. Simultaneous is simultaneous. But in Einstein's universe, this bedrock assumption crumbles. Consider this thought experiment, one that Einstein himself devised in various forms. Imagine a long train speeding along a straight track. A passenger is standing in the exact middle of one of the cars. Two bolts of lightning strike simultaneously, one at the front of the car and one at the back. Now, a person standing on the platform, perfectly aligned with the middle of the car at the moment the lightning strikes, sees both flashes at exactly the same time. The light from each strike travels the same distance to reach her, and since the speed of light is constant, it arrives simultaneously. She concludes correctly, from her frame of reference, that the two lightning bolts struck at the same moment. But what does the passenger on the train see? Remember, the train is moving forward. In the time it takes the light from the two strikes to reach the passenger has moved slightly toward the front of the car. That means the light from the front strike has a slightly shorter distance to travel to reach him, and the light from the rear strike has a slightly longer distance to travel. Since the speed of light is the same in both directions, this is crucial. The light from the front strike arrives first. The passenger sees the front flash before the rear flash. He concludes, correctly from his frame of reference, that the lightning struck the front of the car before it struck the back. Both observers are right. There is no mistake, no miscalculation, no failure of observation. The events genuinely are simultaneous in one frame and not simultaneous in the other. Simultaneity is not objective. It depends on the observer's state of motion. This is, for many people, the most philosophically disturbing consequence of special relativity, even more so than time dilation. Because if two events that are simultaneous for one observer are not simultaneous for another, then the very notion of the present loses its universal meaning. Think about what the present means to you. Right now, as you listen to this, you have an intuitive sense that there's a single shared moment, a universal now, that encompasses the entire cosmos. Somewhere, a star is being born right now. Somewhere, a civilization is rising or falling right now. You imagine a vast cosmic snapshot, frozen in time, and you call it the present. But relativity tells us this snapshot doesn't exist. There is no single now that all observers share. Your present is not the same as the present of someone moving relative to you. And this isn't a matter of communication delay or the time it takes signals to travel. Even after correcting for all such effects, observers in different states of motion will disagree about the order and timing of distant events. The past, the present, and the future, those seemingly iron categories that structure our entire experience of reality, are to some degree a matter of perspective. This is a staggering idea, and we should sit with it for a moment before moving on. because what it implies is that the flow of time, the sense that the present is a moving spotlight, gliding from past to future, illuminating each moment in turn and then leaving it behind, may not be a feature of the universe at all. It may be a feature of us, of our consciousness, of the way our brains, evolved in a world of low speeds and modest gravitational fields, construct a model of reality that is good enough for survival but woefully incomplete as a description of what actually is. Now, at this point, you might reasonably object. You might say, this is all very well in theory, but does any of this actually matter? The speeds involved are astronomical. No human being has ever traveled at a significant fraction of the speed of light. These effects are so small in everyday life as to be negligible. Isn't this just mathematical abstraction? It's a fair question. And the answer is an emphatic no. These effects are real, they are measurable, and they matter in ways that directly affect your daily life. Consider the global positioning system, GPS. You probably used it today. Perhaps you used it to navigate to a restaurant, or to find the fastest route through traffic, or simply to confirm what time it is, since your phone's clock is synchronized to GPS satellites. Those satellites orbit the Earth at an altitude of about 20,200 kilometers, moving at roughly 14,000 kilometers per hour. That's fast by human standards, but it's a snail's pace compared to light. And yet, the time dilation effect predicted by special relativity, the slowing of the satellite clocks relative to clocks on the ground due to their speed, amounts to about 7 microseconds per day, 7 millionths of a second. That doesn't sound like much, but GPS works by measuring the time it takes for signals to travel from satellites to your receiver and converting those times into distances. Light travels about 300 meters in a microsecond. 7 microseconds of accumulated error would translate into a positional error of roughly 2 kilometers by the end of a single day. Your GPS would be useless. In reality, the situation is even more complex, because general relativity, Einstein's theory of gravity, which we'll touch on shortly, produces an opposing effect. The weaker gravitational field at the satellite's altitude causes clocks to run faster, by about 45 microseconds per day. The net effect is that satellite clocks run ahead of ground clocks by about 38 microseconds daily, and this must be corrected for. Without both special and general relativistic corrections, GPS would accumulate errors of approximately 10 kilometers per day. The system would degrade into uselessness within minutes of being turned on. Every time you successfully navigate to a coffee shop, you are, whether you know it or not, relying on the truth of Einstein's equations. But there's an even more direct and beautiful confirmation of time dilation, one that comes not from human technology, but from nature itself. High in the Earth's atmosphere, cosmic rays, high-energy particles from deep space, slam into air molecules and produce showers of subatomic particles. Among these particles are muons, which are essentially heavier cousins of electrons. Now, muons are unstable. They decay. They fall apart, with an average lifetime of about 2.2 microseconds. That's 2.2 millionths of a second. Given their speed, which is typically about 99.8% the speed of light, a quick calculation shows that a muon should travel only about 660 meters before decaying. They're created at altitudes of about 15 kilometers. They should never reach the ground. They should decay long before they get here. And yet, muon detectors at the Earth's surface detect enormous numbers of them. They're arriving in droves. How? Time dilation. Because the muons are moving at 99.8% the speed of light. Their internal clocks, the ticking that governs their decay, are running dramatically slower relative to our clocks on the ground. From our perspective, the muon's lifetime is stretched by the Lorentz factor, which at that speed is about 16. So instead of living for 2.2 microseconds by our clocks, they live for about 35 microseconds, more than enough time to traverse the 15 kilometers from the upper atmosphere to the ground. And here's the truly elegant part. From the muon's own perspective, it lives for exactly 2.2 microseconds, just as the physics predicts. It doesn't experience its life as extended. But from its frame of reference, the Earth's atmosphere is length contracted, squished along the direction of motion by the same Lorentz factor. So the atmosphere isn't 15 kilometers thick, it's less than a kilometer thick. The muon has no trouble traversing it in its brief lifetime. Both explanations, time dilation from our perspective, length contraction from the muon's perspective, give the same answer. They are two faces of the same relativistic coin. Every second of every day, muons created high above us are surviving journeys that Newtonian physics says they shouldn't. They are tiny, ephemeral messengers, and their message is this: time dilation is not a theoretical curiosity. It is the way the world works. So we have time dilation, we have the loss of universal simultaneity, we have length contraction, the phenomenon where objects moving at high speed are measured to be shorter in their direction of motion. These are all consequences of Einstein's two simple postulates, and they are all, in a profound sense, consequences of the same underlying reality. But what is that underlying reality? What is the deeper structure that gives rise to all these seemingly disparate effects? The answer was provided not by Einstein himself, but by his former mathematics professor, Hermann Minkowski. In 1908, Minkowski gave a lecture that began with one of the most dramatic openings in the history of science. Henceforth, he declared, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. That union is what we now call space-time. Minkowski realized that the equations of special relativity could be understood geometrically if you stopped thinking of space and time as separate things and instead thought of them as dimensions of a single, four-dimensional entity. Just as a point in ordinary space is specified by three numbers, its x, y, and z coordinates, a point in space-time is specified by four numbers, three spatial coordinates, and one temporal coordinate. An event is not just where something happens, it's where and when something happens. And just as the distance between 2 points in space is a real, invariant quantity that doesn't depend on how you orient your coordinate axes, there is a quantity in spacetime called the spacetime interval that is invariant for all observers, regardless of their state of motion. This is the key insight. In ordinary space, if you rotate your coordinate system, if you turn the map, the x and y coordinates of a point change, but the distance between any 2 points stays the same. Rotation mixes x into y and y into x, but the underlying geometry is unchanged. In space-time, changing your velocity is analogous to a rotation. It mixes space into time and time into space. When you move faster through space, your time coordinate gets rotated into a spatial coordinate, and your spatial coordinate gets rotated into a temporal one. This mixing is why moving clocks run slow, why moving rulers are shorter, and why simultaneity is relative. These are not three separate phenomena. They are three aspects of a single geometric truth. And here lies perhaps the most beautiful and revelatory idea in all of special relativity. Everything in the universe is always moving through space-time at exactly the same speed. Always, without exception. That speed is the speed of light. Let me say that again because it deserves to be said slowly. Right now, as you sit still, you are moving through space-time at the speed of light. You're not moving through space. You're sitting in a chair, but you are moving through time. And you're moving through time at the maximum possible rate. All of your motion through space-time is directed along the time axis. Your clock ticks as fast as it possibly can. Now, when you get up and start walking, you divert some of your motion from the time direction into a spatial direction. You're now moving through space a little bit, which means you're moving through time a little bit less. Your clock ticks very, very slightly slower than it did when you were sitting still. The difference is, of course, absurdly small at walking speeds, but the principle holds. When you get in a car, you divert a bit more of your space-time motion into the spatial direction, and your clock slows a bit more. In a plane, more still. In a rocket, more. And if you could somehow reach the speed of light itself, which for any object with mass is impossible, as we'll see, you would have diverted all of your motion through space-time into the spatial directions. You would be moving through space at the speed of light, and your progress through time would have stopped entirely. Your clock would not tick. Time would cease to pass. This is why photons do not age. A photon moves through space at the speed of light, which means all of its space-time motion is spatial. It has nothing left over for time. From its own frame of reference, to the extent that concept applies, It exists in a single eternal instant. Think of it as a budget. You have a fixed amount of motion to spend, a cosmic speed limit, the speed of light, and you can allocate it between space and time in any proportion you like. Sit still, and you spend it all on time. Move through space, and you must borrow from your time budget. The faster you move through space, the less you have for time, and the slower your clocks run. This is not a metaphor. This is the literal geometric structure of space-time as described by Minkowski and refined by the mathematics of Einstein's theory. The trade-off between motion through space and motion through time is a rotation in four-dimensional space-time, governed by the hyperbolic geometry of Minkowski space. And the constant that mediates this trade-off, the constant that sets the exchange rate between space and time, is the speed of light. This is why the speed of light is so fundamental. It's not just the speed at which light happens to travel. It is the fundamental speed of the universe, the total speed at which everything moves through space-time, the speed that links the spatial and temporal dimensions into a single inseparable whole. Light doesn't travel at the speed of light because it's special. Rather, what we call the speed of light is the fundamental constant, and light travels at that speed because it has no mass, and therefore allocates all of its space-time motion to the spatial direction. It would be more accurate to call it the speed of space-time, or the speed of causality, than the speed of light. Light merely happens to go that fast. This realization that space and time are not independent, that they are woven together into a four-dimensional fabric, and that our motion through this fabric is governed by a single immutable constant, is, for many physicists, the true heart of special relativity. It transforms a collection of strange and seemingly arbitrary effects, time dilation, length contraction, the relativity of simultaneity, into the natural, inevitable consequences of geometry. Just as the Pythagorean theorem governs the relationship between the sides of a triangle in flat space, the space-time interval governs the relationship between space and time in the geometry of reality. The weirdness of relativity is not weirdness at all. It is geometry. It is the shape of the world. And it is here that we should pause and consider something that Einstein struggled with deeply in the years following his 1905 paper. Special relativity, for all its elegance, has a significant limitation. It only applies to inertial reference frames, frames of reference that are not accelerating. It describes the physics of gliding, but not the physics of pushing. And there is one particular form of acceleration that is so pervasive, so inescapable, that ignoring it renders a theory incomplete. That form of acceleration is gravity. Einstein's general theory of relativity, published in 1915, extends the framework of space-time to include gravity, and it does so with an idea of breathtaking beauty. Gravity is not a force pulling objects together. Gravity is the curvature of space-time itself. Massive objects, stars, planets, even your own body, bend the fabric of space-time around them, and other objects move along the curved paths that this bending creates. The Earth doesn't orbit the Sun because the Sun is pulling it with an invisible force. The Earth orbits the Sun because the Sun's mass has curved space-time in its vicinity, and the Earth is following the straightest possible path, called a geodesic, through that curved geometry. It moves in an orbit not because it is being deflected from a straight line, but because the straight line itself is curved. This idea that gravity is geometry is what necessitates those corrections to GPS satellites that we mentioned earlier. Clocks in weaker gravitational fields, farther from the Earth's center, run faster than clocks in stronger gravitational fields, because the curvature of space-time is less pronounced at higher altitudes. Time literally passes at different rates at different heights above the Earth. This has been measured with spectacular precision. In 2010, researchers at the National Institute of Standards and Technology used aluminum ion clocks, among the most precise timepieces ever built, to detect the difference in the passage of time between two clocks separated by a height of just 33 centimeters. 1 foot. The clock that was higher by 1 foot ticked faster by exactly the amount general relativity predicted. The fabric of space-time is not something abstract and remote. It is right here, in this room, curving gently around you, making the clock on your top shelf tick an infinitesimally tiny bit faster than the clock on the floor below it. But let us return for a moment to special relativity, because there's one more implication of Minkowski's space-time that deserves our attention, one that takes us from physics into the deepest questions of philosophy. If space-time is a four-dimensional entity, if the past, present, and future are all out there as coordinates in this block, just as the north end of a street and the south end of a street are both out there in space, then what does that say about the nature of time? Is the future already determined? Is the past still real? Are we, in some sense, living in a static, unchanging four-dimensional sculpture, and the flow of time is merely an illusion produced by our consciousness as it slides along one axis of this sculpture? This view, often called the block universe or eternalism, is taken very seriously by many physicists and philosophers. In the block universe, your birth and your death are both equally real events in space-time, separated by a certain space-time interval, just as the two ends of a road are equally real locations in space. The distinction between past, present, and future is not a feature of reality. It is, as Einstein himself wrote in a letter of condolence to the family of his lifelong friend, Michel Bessel, a distinction that is only a stubbornly persistent illusion. Bessel had died, and Einstein was offering comfort, or perhaps something beyond comfort, by suggesting that in the eyes of physics, Bessel's death did not mean he had vanished from existence. Bessel's death did not mean he had vanished from existence. He was still there in space-time as much as he ever was. Not every physicist agrees with this interpretation, of course. The block universe raises profound questions about free will, about the nature of consciousness, about why we perceive time as flowing if, in some fundamental sense, it doesn't. These are questions that physics alone may not be equipped to answer. But the fact that Einstein's theory so naturally suggests such questions, the fact that a theory born from the mundane puzzle of why the speed of light is constant for all observers leads inevitably to questions about the nature of existence itself, is a testament to how deeply the theory penetrates into the structure of reality. And now let us come full circle. Let us return to where we started, to the clock on your wall, ticking away with apparent regularity, and to the cup of coffee sloshing in your hand as you walk. The coffee sloshes because you are accelerating. You are changing your velocity, speeding up, slowing down, turning, and the coffee, resisting that change, responds. That resistance, that inertia, is one of the most fundamental properties of matter, and it is the very thing that connects the everyday experience of walking with a cup of coffee to the deepest truths of special and general relativity. Inertia is what makes it impossible for any object with mass to reach the speed of light, because the faster you go, the more energy it takes to accelerate further. At speeds close to light, the energy required grows without limit, approaching infinity. The speed of light is not just a speed limit. It is an asymptotic wall that no massive object can ever reach. And this, too, circles back to the geometry of space-time. As you accelerate an object, you are rotating its four-velocity vector in space-time, tilting it away from the time axis and toward the spatial axes. But the total magnitude of that vector is fixed. It's always the speed of light. You can tilt it further and further, but you can never tilt it all the way to being purely spatial, because that would require infinite energy. The geometry forbids it. The coffee in your cup, with its small but non-zero mass, is bound by this geometry, just as you are, just as the Earth is, just as the stars and galaxies are. We are all moving through space-time at exactly the same speed, differing only in the direction of our motion through this four-dimensional landscape. So the next time you walk across a room with a cup of coffee and it sloshes over the rim, take a moment to consider what has actually happened. The coffee has obeyed Newton's first law, resisting your change in velocity. That resistance, inertia, is the same property that prevents anything with mass from reaching the speed of light. The speed of light, in turn, is not merely the velocity of electromagnetic radiation, but the fundamental constant of space-time itself, the speed at which all things move through the four-dimensional fabric of reality. And that fabric, space-time, is the arena in which all of existence plays out, an arena in which time is not fixed, not universal, not the steady river we imagine, but a dimension as pliable and relative as space, stretching and compressing depending on how fast you move and how close you are to a massive object. All feels I went to the teacher's college, to the stopping of time for a photon, from the survival of muons to the functioning of your GPS, from the relativity of simultaneity to the philosophical puzzle of whether the future already exists. All of this flows from two sentences. The laws of physics are the same in all inertial frames. The speed of light is constant for all observers. Two statements. And from them, a universe. There is a passage in the writings of the physicist John Archibald Wheeler that captures, I think, the right spirit in which to hold all of this. Wheeler wrote that space-time tells matter how to move, and matter tells space-time how to curve. He was speaking specifically about general relativity, but the sentiment applies more broadly. The universe is a conversation between geometry and substance, between the shape of space-time and the things that move through it. And we, you, me, the muons, the photons, the galaxies, are both participants in and products of that conversation. We are patterns in the geometry, ripples in the fabric, temporary arrangements of matter and energy tracing our world lines through a four-dimensional cosmos that is, if the physics is to be believed, far stranger, far more beautiful, and far more subtle than the one our senses present to us. Look at the clock again. Watch the seconds tick by. 1, 2, 3. Each tick feels the same. But now you know something you didn't before. Those ticks are not universal. They are yours. They belong to your frame of reference, your world line, your particular path through space-time. Someone moving relative to you has different ticks. Someone in a stronger gravitational field has different ticks. And the light illuminating the clock face, the photons striking your retina, they have no ticks at all. They are ageless, timeless, hurtling through space at the maximum speed the universe allows, and they will never experience a single moment of time. The universe is not what it seems. It never has been. But the truth beneath the seeming, the geometry, the symmetry, the strange and beautiful logic of space-time is, once you begin to glimpse it, far more wondrous than anything our naive intuitions could have invented. Einstein saw it first, but it was always there, hidden in the ticking of every clock, the sloshing of every cup of coffee, the falling of every photon of light from every star in the sky. It was always there, waiting for someone to look closely enough to notice.